Welcome back. In this lecture, we will address certain limiting cases of the Butler-Vomer equation. In the previous lectures, we had analyzed single and multi-electron electrochemical kinetics via the Butler-Vomer equation. While that treatment is comprehensive, it is not typically useful in practical analysis of experimental systems. So we will look at two important limiting cases called the Tafel approximation and the linear approximation. And we'll also introduce the effect of transport on electrochemical kinetics. We'll deal with transport much more elaborately from the next lecture, but this gives you an introduction to the effect of transport. We had earlier seen that the net current versus the potential shows this behavior. The overall current provided by the green curve is the sum of two components, oxidative current and the reductive current. You see that there are two limiting behaviors. The green curve can be approximated by the red curve when you are in this regime, and the green curve can be approximated by the blue curve when you are in this regime. So far from the null potential, either in this direction or in this direction, there are approximations to the green curve, namely that the two exponentials of the Butler-Vomer equation need not be utilized, and a single exponential is good enough for approximating the green curve. So this is a single exponential, this is a single exponential. Therefore, in these two regimes, far away from the null potential, just mathematically, one exponential is good enough for representing the overall current. So if you look at the oxidative side of the current, the net current can be represented in this manner. This is the surface over potential in the anodic region. This can be rewritten in the following manner. This is the way we typically plot when the over potential is significant. So we'll elaborate further what we mean by significant. So this can be rewritten for the first time. This was rewritten by Tafel long time ago. And all these inferences was made via experiments. Okay, so because when you plot it, it's easier to plot in a log plot compared to a log plot. This equation can be written in this manner, and you get these two constants within this approximation. What is the approximation? When eta is significantly large. It's useful to have in mind the value of this constant at standard condition, which you will see this number 59 millivolts per decade often in many analysis, not just in electrochemistry, but also in semiconductor physics, plasma physics, and so on. So that's a good number to have in mind. Why is this important? This kind of a plot is going to give you an idea for alpha A, right? So what is that? Available under the experimentalist control? You can change this as a function of the over potential. You can measure I, right? So when these two are available to you, from this kind of a plot, you can get an idea of what is alpha A. That is the utility of this kind of analysis. As we had discussed earlier, alpha is a measure of important measure of reaction kinetics. We had earlier, in the previous lecture, we had mentioned order of reaction as well as alphas to be important measures of electrochemical kinetics. And these are, in practice, these are obtained via experiment. And this kind of analysis is going to be useful for getting alpha A. A similar thing, analysis can be made in the cathodic region, and you can represent the net current by a single exponential in the cathodic region. Here you have alpha C. Because of the sign convention, you should remember certain things. In electrochemistry, to bookkeep the signs is hard, okay, because there is certain kinds of sign convention which evolve because of the history, the way the field developed. So it is not often very intuitive, these sign conventions, but you should bookkeep the sign conventions carefully. Okay, so the reductive current is given a negative sign, as you can see here, and you have to contrast. There's a positive sign, contrast the behavior in the anodic region with the behavior in the cathodic region. Okay, so the sign of the O potential is also different. Okay, so on one side you say the O potential is a positive quantity. On the other side, you say O potential is a negative quantity on the cathodic side, and the current which you get is also a negative quantity. Again, you can have a plot in the cathodic region, and such a plot would help you get alpha C. Both these things are put together into a single plot. This is a very famous plot in experimental electrochemistry called the Tafel plot, and the Tafel approximation is valid when you are far from the null potential. Okay, so there is a point where the anodic and cathodic current is one and the same. That is the null potential. That gives you, that helps you find out I naught. And as you move far away, so what is far away? Typically, as a rule of thumb, if the absolute magnitude of the surface over potential, either in the anodic region or the cathodic region, because we are just talking about the modulus of the over potential. If the modulus of over potential is more than 100 millivolts, the Tafel approximation is valid, and you can represent the current via the Tafel approximation. Okay, so the Tafel approximation is something like this, right? You can represent eta using these two terms. So just a single exponential is good enough for representing the overall behavior. It helps you get the so-called Tafel constants, alpha C and alpha A. There is another approximation which is also valid, which is also useful. This is used in the regime when the absolute magnitude of the O potential is quite less. Just to contrast, when we say the O potential is large, we are talking about this magnitude. And when we say the O potential is small, we are talking about this magnitude. In this regime, the Butler-Vomer equation can be represented as a Taylor series. You can expand the exponential via a Taylor series around zero. So the exponential will be represented by two terms. These are the two terms. And when you add them up, you get this kind of an expression. Okay, so I naught is approximated this way. It is equal to I naught alpha A plus alpha C F by RT eta S. Okay, so this is an approximation that is useful at low potentials. Okay, so these are two regimes. Typically, at low potential, you use the linear approximation for the Butler-Vomer equation. At high O potential, you use the Tafel approximation to the Butler-Vomer equation. These are fairly useful in the experimental analysis of electrochemical systems, electrochemical kinetics. We'll move on. This is our first introduction to the effects of mass transport on electrochemical kinetics. So in the next few lectures, probably next lecture will also be on electrochemical kinetics, but following the next lecture, we'll do a series of lectures on electrochemical transport. Let's just pause and see where we are. Okay, so we introduced electrochemical systems, and then we looked at the thermodynamics of electrochemical systems. In the last few lectures, we looked at electrochemical kinetics. The last segment that addresses the fundamentals of electrochemical systems is the transport of electrochemical systems. We're just introducing one particular aspect, but we'll do a series of lectures on transport of electrochemical systems. Okay, so let's look at this particular system. So what do we have here? So on the x-axis, we are plotting the distance from the electrode surface. At the electrode, this particular reaction occurs. There is a reduced system which gets converted to an oxidized system. Let's just pause for a minute here. Yeah. So R and O refer to a reduced species and an oxidized species. When you add electron to the oxidized species, you get the reduced species and the other way around. Because this reaction occurs on the electrode surface, if you plot the concentration as a function of distance, you see this profile. Okay, so this is the concentration of the reduced species in the bulk. This is the concentration of the oxidized species in the bulk. Okay, because the reduced species gets consumed at the electrode surface, the concentration of the reduced species near the electrode surface is less, because of which there will be a transport of the reduced species from the bulk to the surface of the electrode, where it gets consumed. The opposite behavior is seen for the oxidized species, because the oxidized species is generated at the electrode surface. The concentration of the oxidized species at the electrode surface, that is indicated by COS. This S indicates the electrode surface. Okay. So the concentration of the oxidized species is greater near the electrode surface, because of which there is the transport of the oxidized species from this regime closer to the electrode surface to the bulk of the system. All right. So a general way of indicating the mass transfer fluxes is via this kind of an equation. So probably chemical engineers are familiar with this kind of equation, but it's a simple equation wherein we denote, for example, in this case, the flux of reduced species is given by a mass transfer coefficient times this is a greater number, a larger number, and this is a smaller number, right? So this would be a positive quantity. A mass transfer coefficient is also a positive quantity. The overall flux is given by in this manner. Okay, so a lot of theories have gone into getting expressions for mass transfer coefficient. We won't go into those things in this lecture, but we'll just say that the mass transport can be represented in terms of concentration difference times the mass transfer coefficient. These fluxes can be converted into a current by multiplying it by the Faraday constant. So that's you get this quantity, and at steady state, what is being transported from the bulk gets consumed by the reaction at the surface. This is the Tafel approximation to the Butler-Vomer equation. So what is getting transported from the bulk gets consumed at steady state because of the reaction on the electrode surface, right? Just to make the analysis easier, we take this quantity, the reference quantity, to be that of the bulk concentration. Okay, so you need some reference concentration. You take that to be the bulk concentration. Okay. Because the concentration on the electrode surface is a hard to measure quantity, what is more easily measured is or calibrated are these two quantities, because these two quantities are hard to measure properties. You, from these two equations, you eliminate CRS. Okay, so you eliminate the concentration of R at the electrode surface, which you can do, and you can rewrite I in this manner. Okay, just from these two equations. Let us pause for a moment and look at the form of this expression. Typically, all this expression on flux, okay, is correlated to resistances. Okay, so here, what are the true resistances? One by this quantity is a measure of mass transfer resistance. Okay, so there are two resistances here. There is a resistance for mass transfer and resistance to electrochemical reaction. These two resistances add up in series. Okay, so 1 by R, the total is given by 1 by resistance to mass transfer plus 1 by resistance to electrochemical kinetics. Okay, if Km is large, if that is the mass transfer coefficient is large, then the resistance to mass transfer is less. Therefore, 1 by this term will be a small quantity, so you can neglect this quantity. So the overall resistance can be approximated by the resistance to electrochemical kinetics. Okay, so if Km is large, this can be neglected, and because this is going to be a small quantity, and you have only this particular quantity. When is that true? When eta s is relatively small. Okay, so one way to decrease relatively the resistance to electrochemical reaction is by increasing eta s. So we will look at that. Okay, so when eta s is increased, this particular quantity becomes large, then the resistance to electrochemical kinetics becomes small. Therefore, you can neglect this particular quantity and you will retain this particular quantity. Okay, so let me backtrack a minute. Okay, so I had said that 1 by R. Okay, so that's not the right thing. These two resistance add in series, right? So it is R total, that is the total resistance, is equal to mass transfer resistance plus the resistance for electrochemical kinetics. Okay, just to correct. Okay, I just made a statement. It is 1 by R. It's not true. It's the R total. The overall resistance is given by resistance to mass transfer, that is this quantity, and resistance to electrochemical kinetics, that is this quantity. All right. So when we increase eta S, we are in effect decreasing the resistance to electrochemical kinetic. So you are making the reaction more facile. So when you make reaction more facile, on relative terms, you are able to decrease the resistance to electrochemical reaction, and on relative terms, this quantity dominates. Okay. So when this is a large quantity, 1 by this quantity is a small quantity. So what is retained is this quantity. So if Km is large, 1 by Km is small. If Km is small, 1 by Km is large. Okay, so that's the argument we make. So at large eta S, we can neglect this and you are going to retain this quantity alone. So if you plot I versus eta S, you see this kind of a behavior. So at small eta S, you still retain this quantity because your resistance to electrochemical kinetics is still significant. Okay, so you retain this quantity and on relative terms neglect this quantity. But when eta S becomes significant, what dominates the resistance is just the mass transfer resistance. When you neglect this, what you see is that you see I plateaus off, right? Why is there a plateauing off of I? That is the important thing here. It plateaus off because all these things are constant terms, right? So Km is mass transfer coefficient, that's a constant term. Bulk concentration, that's a constant term. These two are, of course, constant. Okay. So what you see is that I limiting current. Okay. So if you normalize I as divided by this particular quantity, this is called the limiting current density. I limiting current density is given by NF, mass transfer coefficient, times the concentration in the bulk. Okay. So that's what you observe here. Okay. So this is a very important behavior. This is observed in many systems. You typically will introduce something called the supporting electrolyte. Okay. When we discuss the transport in electrochemical systems, we will address something called a supporting electrolyte. Even with supporting electrolyte, when the surface over potential is significantly large, you observe this kind of limiting behavior. It's called the limiting current density. It's going to be very important And the reasons for limiting current density is the following. Okay, on relative terms, the resistance to electrochemical kinetics, okay, this particular term can be neglected, and the only resistance that comes into play is the resistance to mass transfer. Therefore, the overall current can be represented in this manner. This is just an introduction to the effect of mass transfer in electrochemical systems, but we will elaborate these kind of arguments much more in the next few lectures. Overall, in this lecture, we have looked at two things. One is that the Butler-Vomer equation has two exponentials. But in practice, we can use certain approximations, namely two approximations. One approximation called the Tafel approximation, which is valid at higher overpotential of the order of 10 millivolts. And there is another approximation which is used when the absolute magnitude of surface overpotential is of the order of 10 millivolts. That's called the linear approximation. Okay, so using these two approximation, a simpler form of Butler-Vomer equation is obtained, and that is useful for getting alpha A and alpha C's. Okay, so this is very useful, and we made a first cut introduction to the effect of transport in electrochemical systems. In this particular case, electrochemical kinetics, we saw at high enough eta S, there is a limiting behavior to current density. Even when you increase the overpotential, the current no longer increases, and that limiting current density is a constant. It can be expressed using the mass transfer coefficient and the bulk concentration of the reactant. With this, we will wrap up this lecture. We need to be addressing one particular aspect of electrochemical kinetics, which we will do in the next lecture. And following that, we'll do a series of lectures on transport in electrochemical systems. Thank you.